Over $500 billion in global trade depends on one industry. And that number hides something far larger. This $500 billion industry dictates the flow of more than $10 trillion in global trade. More than 90% of advanced chips are produced in a single region. A single factory outage could cost the world trillions. Every missile, every AI model, every modern economy now runs on silicon measured in nanometers. The United States designs the most advanced chips on Earth. It controls the software, it controls the machines. Yet it manufactures less than 15% of global supply. China consumes more than 35% of all chips produced worldwide, more than oil, more than steel. Yet it cannot freely produce chips at the most advanced nodes. One export restriction from Washington can stall entire sectors of China's technology industry overnight. And the most powerful players in this story are not even American or Chinese. TSMC produces the world's most advanced chips. ASML builds machines so complex that no other country has been able to replicate them. What appears to be a supply chain is in reality a map of geopolitical leverage. The United States chose to control the peak of technology. China chose to rebuild the mountain from the ground up. When a microscopic chip becomes a strategic weapon, who is shaping the future? The nation that controls the summit, or the one willing to endure the climb? The semiconductor race did not begin as a commercial ambition. It began as a military requirement. For the United States, chips emerged from war, not markets. Early computers, radar systems, missile guidance, encrypted communications, all demanded components that were faster, smaller, and more reliable than anything before. Silicon was not a consumer product. It was a strategic asset. During the Cold War, American semiconductor leadership formed inside a unique ecosystem. Universities conducted research, defense agencies funded experimentation, private companies transformed prototypes into products. The system did not move by central design. It moved by alignment. Military demand created funding, funding enabled research, research spilled into civilian markets. What mattered most was not volume, it was control. Control over design, over architecture, over standards. The assumption was simple. If the United States stayed ahead technologically, manufacturing would follow. For decades, that assumption held, but the same logic that built American dominance also reshaped it. As globalization accelerated, semiconductor manufacturing changed. Fabrication became capital-intensive. Margins narrowed. Production moved to regions willing to absorb cost and risk. Design stayed. Software stayed. Manufacturing slowly moved outward. The system optimized for efficiency, not for resilience. China entered the semiconductor story from a different position. For China, chips were never about technological prestige. They were about dependence. By the early 2000s, China had become the world's manufacturing center. Factories assembled phones, servers, and network equipment at unprecedented scale. But the most critical component inside those products came from elsewhere. Each year, China spent more importing semiconductors than importing oil. At first, this dependency appeared manageable. Global supply chains were stable, access was open, trade was predictable. That stability did not last. As China moved up the value chain, chips changed meaning. They were no longer a cost item. They became a strategic vulnerability. Artificial intelligence, advanced manufacturing, telecommunications, military modernization, all converged on the same bottleneck. Unlike the United States, China could not rely on markets alone to close the gap. The distance was too large, the timeline too long, the barriers too high. Semiconductors offered no shortcuts. You could not buy what you were denied. You could not copy what you could not see. You could not innovate freely inside a system controlled by others. This is where divergence became structural. For the United States, semiconductors evolved into leverage, a way to maintain advantage by controlling the narrowest points of the technology stack. Design software, advanced manufacturing tools, cutting-edge architectures. For China, semiconductors became a question of survival. Not ideological survival, operational survival. Without domestic capability, every technological advance remained conditional. One system trusted openness, specialization, and global integration. The other prepared for constraint, denial, and long-term pressure. Neither path was chosen suddenly. Neither was purely ideological. They emerged from different risks, different starting points, different definitions of security. And once those paths were set, reversing them became difficult. In semiconductors, the past does not disappear. It accumulates. Experience compounds. Mistakes harden. Advantages reinforce themselves. By the time chips became a geopolitical weapon, the foundations were already in place. What followed was not a sudden confrontation. It was the delayed outcome of two systems that had been moving apart for decades. The divergence did not stop at motivation. It deepened in execution. For the United States, the strategy was not to build everything. It was to control the narrowest points of the system. American power concentrated at the top of the semiconductor stack. Design came first, architectures that defined how chips think, standards that determined compatibility, ecosystems that others had to follow. Software became the gatekeeper, design tools, simulation platforms, verification systems. Without them, advanced chips could not be created at all. Manufacturing, by contrast, was treated differently. Fabrication required massive capital, margins were thin, risks were high, returns were slow. As long as production remained accessible, control was unnecessary. This is where specialization took over. The United States allowed manufacturing to migrate, not as a retreat, as an optimization. Design stayed domestic, software stayed domestic, critical tools stayed domestic. The most advanced production moved offshore, but not out of reach. That structure allowed companies like NVIDIA to focus on architecture rather than factories. It allowed firms like Intel to oscillate between design and manufacturing as conditions changed. Most importantly, it preserved control without owning every step. For China, execution followed a different logic. There was no narrow point to control. There was only a gap to close. China entered the semiconductor race without legacy advantages. No dominant design tools, no leading architectures, no advanced manufacturing equipment. What it had instead was scale, capital, and time. The response was not incremental, it was systemic. State funding surged, industrial policy aligned priorities, talent programs redirected human capital. Manufacturing came first, not because it was easier, but because it was unavoidable. Without domestic production, every other layer remained dependent. Factories were built, process nodes improved gradually, yields increased slowly. Progress was uneven, costs were high, failures were frequent. But the objective was not immediate parity, it was continuity. China accepted inefficiency in exchange for control, accepted duplication in exchange for resilience, accepted delay in exchange for autonomy. Companies like SMIC became symbols of that approach, not because they matched the most advanced global players, but because they reduced exposure. This difference defined everything that followed. The United States built leverage by controlling access. China built capacity by absorbing pressure. One system optimized for peak performance, the other optimized for survival under constraint. Neither approach was cost-free. American control relied on openness remaining selective, Chinese capacity relied on patience remaining political. But both strategies shared one assumption, that semiconductors were too important to leave to chance. By the time export controls arrived, the paths were already locked in. What appeared to be a sudden escalation was, in fact, execution reaching its logical conclusion. The methods did not react to the confrontation, they produced it. The consequences did not appear immediately, they accumulated. For the United States, control delivered leverage. Advanced chip design remained concentrated, critical software stayed restricted, key manufacturing tools remained inaccessible without permission. Export controls amplified that position. Entire product lines could be paused, research timelines could be delayed, investment plans could be rewritten overnight. The effect was visible. American firms retained leadership at the technological frontier. AI accelerators advanced. High-performance computing pushed forward. But leverage carried costs. Global supply chains fractured. Companies faced compliance burdens. Allies were forced into alignment. Manufacturing concentration created new risks. When production clustered in a few locations, resilience weakens. Efficiency had come at the price of redundancy. The system that once optimized globally now required political management. For China, the consequences were different. Advanced progress slowed, access narrowed, external dependence became explicit. But pressure reshaped priorities. Investment intensified, domestic substitution accelerated, tolerance for inefficiency increased. What mattered was not immediate performance, it was continuity. Legacy chips expanded, mature nodes scaled, internal supply stabilized. China did not close the gap at the frontier, but it reduced exposure across the base. The system adapted, design pathways diversified, manufacturing competence deepened, institutional memory formed, constraints forced discipline, failures became data, delays became experience. Isolation became a training environment. Neither side achieved a clean victory. American control remained powerful but brittle. It depended on coordination, compliance, and geopolitical alignment. Chinese capacity grew resilient but uneven. It traded speed for independence, precision for scale. The market adjusted. Companies restructured supply chains, countries reassessed dependencies. Technology planning absorbed geopolitics. What once moved by price now moved by permission. Semiconductors stopped being neutral inputs. They became strategic instruments. The result was not decoupling. It was segmentation. Two systems continue to trade, but with boundaries, with conditions, with risk priced in to every decision. Over time, this reshaped behavior. Innovation slowed at the margins. Redundancy increased at the core. Efficiency gave way to security. The industry did not collapse, it hardened. And in that hardened system, choices made years earlier began to surface as costs. Not theoretical costs, operational ones. Costs paid in capital, in time, and in flexibility. What chips had become was no longer just technology. They were constraints made visible. The semiconductor confrontation was never about chips alone. It was about control. Control over time, over capability, over what remains possible when access disappears. For decades, the global technology system assumed neutrality. Components flowed, markets optimized, efficiency ruled. That assumption no longer holds. Semiconductors have become conditional. Access depends on alignment. Innovation depends on permission. Scale depends on politics. The United States controls the summit. It sets standards, defines architectures, restricts the narrowest points of the system. That position offers unmatched leverage, but leverage requires maintenance. Allies must remain aligned. Supply chains must remain coordinated. Political consensus must remain intact. Control is powerful, but it is not effortless. China continues the climb, not toward immediate parity, but toward insulation. Each factory reduces exposure. Each iteration builds memory. Each failure becomes instruction. The pace is slower. The cost is higher. The outcome remains uncertain, but dependence is shrinking. This is the paradox of the current moment.